Okay, so all right. What I was saying is, in the last session, we finished walking through the practice and credit assignments for the first week, and in the today's session, we are planning to resume from where we left last time. So today we'll start practice and graded assignments for week two, and let's see if time permits, we'll also see if we can do a few questions from week three as well. So I'll quickly start sharing my screen, and we'll start with the practice based assignments for week two first, and then we'll go to graded assignments. Can someone please confirm if my screen is now visible and you are able to see week two practice assignment?
Yeah, we are. Thank you.
Okay, great.
Yes, sir.
All right, so week two, I guess it is entirely related to number system, and we had a detailed discussion on number system as well, where we discussed about several techniques that you can follow in order to convert one system into another. So there were precisely 6 or 7 conversions that we learned in that session: uh, decimal to binary, decimal to hexadecimal, and so on. So there are probably many questions that we'll get based on those lines in this particular assignment, as well as in the graded assignment for the same week. So let us get started for the first question we have. So right now we are given a number 877. As you can see in the subscript, 10 is what is mentioned in the subscript here. So this represents that this number is in the decimal form, and we have to convert this decimal representation into binary. We are given certain options here, and we have to find out which one of these is the correct binary representation for this decimal representation 877. Well, as you know, binary representation can only have 2 digits, 0 or 1. So with that in mind, the first two options are anyway eliminated. So we'll have to find out which of the options, third or fourth, is the correct binary representation for this 877 number. So does anyone remember how do we convert a decimal number into a binary representation?
Division, right? I think
Exactly. We
the
have to
form.
use a long division method. So there was one shortcut rule that we also discussed in that session, is that if you have to go out of the decimal representation, you always have to do division. Whereas if you want to come to the decimal representation from any other octal, binary, or hexadecimal, you will have to perform multiplication. But right now we are going out from decimal. We are going from decimal to binary. So we will be doing division. We will be using long division method. And which number we will be dividing this 877 with?
2.
We'll be dividing it by 2. The reason is we are converting it into binary. If we had been converting it into, let's say, an octal number, then we would have done this division using number 8, because 8 is the base for octal and 2 is the base for binary. So I'll just write that number here, 877. I'll draw those 2 lines. I'll create partitions.
I think what would help us if you can share the screen, we can follow.
Okay, looks like I forgot to share my screen. I'm sharing it. So what is the issue? Okay, looks like I'm not sharing my entire screen. So is my paint screen visible?
Yeah, it is now. Thanks.
All right, I don't know how many partitions we'll require, but anyways, let's see. So 877 is the number, and we are going to divide it with 2. So let's do it. It is going to be 4, 3, and what should be the next digit here?
3.
Are you sure?
Sorry. 3 is 6, 17, 8.
Exactly. So it would be 8, and we will get 1 as the remainder, right? 7 is an odd digit. So 1 is going to be the remainder. 438 is an even number, so we'll get 0 as the remainder, but it is going to 2, 1, and 9. So remainder will be 0. Then we have 1, 0, and then we have 9. Then it is going to be 1 as a remainder. Then again 2. It is going to be 5, 4. It is going to leave 1 as the remainder. 2, 27. It is going to leave 0 as the remainder. Again 2, 1, and 3. It is going to 1 or leave 1 as the remainder. Then 2, it is going to go by 6. It is going to leave 1 by the remainder. Then we have 2, then 3 here. It is going to leave remainder 0. And then finally, okay, so it will cancel 3 by 1 and it will leave the remainder as 1 as well. So now we have divided this entire number 877 and our quotient has come down to 1. So we have to reduce the quotient to either 0 or 1 in case of binary. We have already reduced it till 1, and now we should be able to get a binary representation or the required answer. So can someone tell me, how should I start interpreting this binary representation? From the top or from the bottom?
Bottom.
Exactly. So I should start interpreting it from the bottom because this is going to be my most significant bit, right? This is what we call as MSB. And this is what we call as a LSB, that is least significant bit. So we shall start reading the number from MSB. So it is going to be 1, 1, 0, 1, 1, 0, 1, 1, 0, 1. So how many digits do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 digits here. Let us see what is the correct number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, all have basically minimum 10 digits. So we have to find out 1, 1, 0, 1, 1. So 1, 1, 0, 1, 1. Okay, third option is the correct one because we can see 1, 1, 0, 1, 1 or yeah, 1, 1, 0, 1, 1 is the basically correct representation. It could also have been correct because you can put any number of leading zeros in front of it. But right now you can see you cannot put any extra one here. So you can see these 3 ones which are not there in our representation. There are only 2 ones initially if we start reading it from the MSB. So third option is the correct one. I hope you are all able to understand. So let me also confirm the last 5 digits, 0, 1, 1 and 0, 1. 0, 1, 1 and 0, 1. Yeah, fine. Is that okay? Shall we move forward? Any doubts with this question?
No, please.
All right.
Please go on. Yeah.
Shall assume that is okay, fine. So consider a 10-bit integer number using signed magnitude concept. Identify its positive and negative ranges. So I hope you guys remember that there are 2 conventions through which we represent negative numbers in computer memory. One is signed magnitude. And what is the other one? One is signed magnitude. What is the other convention that we use in order to represent negative numbers in computer's memory?
You take the negative and append to the positive part of it.
What do we call that?
The terminology.
So it is 2's complement,
Okay.
right? And which one is being followed widely these days? And or you could say which is the convention that is being followed by computers in today's world? It is going to be 2's complement, right? 1's complement is not anymore followed. So the advantage that we get in case of 2's complement is when we start representing the numbers on number line. So what the problem in signed magnitude is that 0, this number 0, it basically gets 2 representation, right? One is going to be 0, 0, 0, 0, all zeros, whereas the other representation is going to be 1. The most significant bit is 1 and rest all are 0. So this is the problem. Here 0 number itself gets 2 representation. Whereas in 2's magnitude, in 2's complement, we basically didn't let that happen. And what we do is, instead of giving one more representation to 0, we add one more number in the negative range, right? So 2's complement has basically one more number or one more element included in the negative range. If we say that the positive range is going to last from 0 to 2 power 9 minus 1 for positive, then in case of negative, it is going to range from minus 2 power 9 to minus 1. So if I come back to this question, if we have to find out for sign magnitude, well, it is going to remain the same for both negative as well as positive range. It is going to be, okay, it is going to remain the same. That is going to be this, the first option, where positive range is going to last from 0 to 2 power 9 minus 1. And so the negative range as well, minus 1 to 2 power 9 minus 1. Whereas if we had been doing it for 2's complement, there the negative range would have been from minus 1 to minus 2 power 9. This minus 1 wouldn't have been there because in 2's complement, we only get one representation for 0, which was not the case with signed magnitude. So signed magnitude is easier to understand because you just have to consider MSB, and the rest of the representation has to be interpreted as any other normal binary representation. It might be easier to understand, but of course there are some shortcomings for that kind of convention, and that is why it is not being used. Is that okay?
Yeah.
All right. So coming on to third question. Which of the following ranges describe the negative range for 32-bit hexadecimal representation using 2's complement notation? So I think this has been directly taken from the slides. I believe okay, either of third or fourth. Okay, the third one is going to be the correct option, which is going to start from 8, 7 zeros, and then go till the end of this 32-bit hexadecimal representation. That is how 2's complement numbers are represented in a 32-bit hexadecimal representation. So this is being directly taken from the slides. You can refer to slides as well for this question. Nothing that you need to solve here in order to find out what the answer is. All right. So fourth question, you will probably have to do some calculations here. Suppose you have a document which contains only uppercase alphabets. How many bits are required to encode a character such that the size of the document is minimum? Remember, it says the document has only uppercase alphabets, right? That means uppercase A to uppercase Z. And how many characters do we have in English?
$26, sir.
Yeah, correct. We have 26 characters in English language. I'll just write it here. 26 characters, right? That is from A to Z. Similarly, if you count small a to small z, then we will get 52, 26 plus 26. Apart from that, we have 10 digits as well. That ranges from 0 to 9. All right, but as far as this question is concerned, we are only going to be concerned about these 26 characters, capital A to capital Z. That's it, right? These small a to small z is none of our concern here. Now, we are also given some notes here. You can create your own encoding method. Fine. Document contains all uppercase alphabets. Okay, this is already given in the question statement. Code for each alphabet should be of the same length. Right. This is also an important instruction. So, can someone tell me how many bits would you require at minimum in order to encode all these 26 characters? Because this is what we have in the document. Any idea? How would you do that, or how would you solve such kind of questions? Okay, so there you have to remember the powers of 2, right? For example, if you just have one bit, or I would say if you just have one bit, then what you can do is, or how many characters you can encode. If you just have one bit available, you can encode 2 power 1 characters. So 2 power 1 means what? What will be the answer? It is going to be 2. That means you can encode 2 characters if you have 1 bit available. Whereas if you have 2 bits available with you, how many characters you can encode? You can encode 4 characters. Right? How would you do that? I think we have done that many times. 0, 0, 0, 1, 1, 0, 1, 1. right? So you have encoded 0, 1, 2, 3 in binary here. Now, if you have 3 bits available, how many characters can you encode?
8.
Exactly, you can
8.
encode 8 characters here, right? Again, for that, we can write here 0, 0, 0, 0, 0, 1, 0, 1, 0, so on. We'll go till 1, 1, 1. You can find out the binary representations for 2, 3, 4, 5, 6, etc. If we have 2 power 4, how many characters can we encode? We can encode 2 power 4,
16.
that is 16 characters, right? And if we have 2 power 5, we can encode 32 characters. If we have 2 power 6, we can encode 64 characters, right? So this is how you find out that how many characters you can encode if you have so many number of bits available. Coming back to our question. So here we have to encode how many characters?
26.
We have to encode 26 characters. So we cannot go by 2 power 1, or we cannot encode all those characters with 1 bit, because the maximum number of characters we can encode if we have 1 bit available are 2. We cannot go with this. We cannot go with 4. We cannot go with 8. Can we go with 16?
No, sir.
No, we cannot go with 16. So the nearest possible number of bits that satisfy a requirement is what? 2 power 5. Right? 2 power 5 can take care of 32 characters. Yes, we just need to encode 26. We are still having excess of 6 more characters here, but that is fine. We cannot go with 2 power 4 because it only allows us encoding for 16 characters. So the minimum number of bits that we require in order to encode 26 characters, or a document which only has uppercase English alphabets, we will be requiring a minimum of 5 bits there, right? 2 power 5, 32. So we'll be requiring a minimum of 5 bits. So the answer is going to be 5 here. Is that okay?
Now, what
sir.
is the significance of those notes?
So sometimes people, get confused that how can you create your own encoding algorithm. For example, if they have just, learned about 8-bit representation, that means every number has to be represented with 8 bits only, then they will probably question how can you write 0, 0? How can you write 0, 1? Like you will have to extend it till, or you will have to add 6 more leading zeros here, 6 more leading zeros here, in order to make it a valid, what you call as binary representation. This is a notion that people generally follow when they start learning about, bits and these things initially. So that's why we thought of just mentioning this as a note, that it is possible for you to even write your own encoding method.
Okay, let's move on. Yeah.
Okay, so which of the following assembly level instructions can be used to store a value of 0 in a register named R2, assuming R0 always holds the value 0 and R1 always holds 1? So we have to store a value of 0 in R2 register. That is what our objective is. So move R2 0. What this instruction is going to do is it is going to copy this value and it is going to paste it in the R2 register. So this is one of the correct options, no doubt. Coming on to the second instruction, what it says is, it says add these two operands, 0 and 0, and put the result back into R2 register. So this is also a valid instruction in order to store 0 value in R2 register. That's perfectly valid. Coming on to third instruction, it says subtract. That means subtract R1 and R0 and put the result back into R2. So what is the value stored in R1?
1.
1.
R1 is 1, R0 is 0. So 1 minus 0 is what? 1.
1. So it's
So
wrong.
we are storing 1 in R2. That's not correct. We wanted to store 0. So that is not a correct option. Coming on to this add I. So what it does is add immediate. Okay, add I think I'll have to check once. Okay. It takes an immediate value as well. Fine. So here, what are we doing is we are adding these two immediate values. Instead, one immediate value and one is a register value. For example, in add, we used two immediate values, 0 and 0. Here we are taking 1 as the immediate value. So R1, what is the value of R1?
1.
R1 is
One.
basically having 1, and we are adding it with 0. So 1 plus 0 will become 1, and you are storing 1 in the final register, that is R2, which is also not correct. So only the first two options are correct, where we are able to store 0 in the R2 register. I hope this is okay. All right, so maybe we can move to next question. So collection of 4 bits is called,
Byte.
Nibble.
that is collection of 8 bits.
Nibble.
So byte is collection of 8 bits. Yeah, nibble is called a collection of 4 bits.
Oh, collection of 4 bits. Okay.
All right, so what is the decimal equivalent of binary number 1011.0101? Okay, so we will have to find out what is the decimal equivalent of this. So does anyone remember how do we do that? How do you convert binary back to decimal? We have already seen decimal to binary, but how do we do the vice versa?
Yeah, from the left to right, it's a multiplication.
Exactly, we'll have to do multiplication this time. So 1011 and 010. 1011 010. All right, so what we will have to do here is we will have to do multiplication, and I'll just write powers here so that you don't get confused while writing those equations. This is going to be 2 power 0, this is 2 power 1, 2 power 2, 2 power 3. What will we do on the right side of this decimal? Doesn't even remember. What will we do with the values that are written after the decimal here? How do we?
2 to the power minus 1.
Exactly. So we'll go to minus 1, minus 2, minus 3, and minus 4. So let us start. I would write here 2 power 3 multiplied by what? What should it be multiplied with?
2 to the
1
power
or
3.
0?
Okay, sorry.
So 3 is written just below 1. So this will be multiplied with 1. Now 2 power 2 multiplied with what?
0.
Because 2 is written below 0. Then 2 power 1 multiply what?
1.
Then 2 power 0 multiply by what? 1. Then plus 2 power minus 1 multiply by what? 0. Then 2 power minus 2 multiply by what? 1. 2 power minus 3 multiply by 0. And 2 power minus 4 multiply by 1. Okay. Now we just have to do classic mathematical calculation. So 2 power 3 is 8. I'll write 8 here. I'll simply leave out all these zeros, which are going to yield 0 here. For example, this. For example, this. This. I think we only have 3 zeros here. Yeah, so I'll just leave out all the zeros. So 2 power 1 into 1, what will we get? 2 power 1 into 1.
2.
It is going to be 2. Similarly, 2 power 0 into 1.
1.
It's going to be 1. Now we have already left it out. So 2 power minus 2 into 1. What is it? 1 divided by 2 power 2. So that means
0.25.
1 by 4. Yeah, it is going to be 0.25. I'll just write it this way for now. And we have 2 power minus 4. So I'll write it as 1 divided by 60. So 8 plus 2 plus 1, it is going to give us 11. And we are going to get 0.25. And what this 1 by 16 is going to be? Can someone please do the calculation for me? Okay.
0.625. 0.6.2.
0.0625. Fine. All right. So we have 11 point what? So we have 11.20. That is going to be 2 only. 5 and 6. Okay. I think it will become 3. So 5 and 6 will become 11, and 1 will be carried to this 2. That is fine. And then we will have 25. So 11.3125 is going to be the answer. Okay, fourth option. Is that understood to all? How do we convert a binary number back into decimal? Is that okay? Shall we move forward?
Yes, sir.
Okay. Fine. Okay, so this is another question based on binary calculations. So the sum of two unsigned binary numbers is this. If one of the numbers is this, what is the value of other number? Can someone tell me, or can someone give any hint? How do we do this? We are given a sum. We are given one of the numbers for which the sum is already given along with another number, and we have to find out the second number. So what I can say here is we are given x plus y. It is something. We are given x. We have to find out y. How would you do that in classic mathematics?
Subtract the known from the sum, na?
Exactly, this is what you would do. You would subtract x from x plus y. So x plus y minus x. This is going to yield x, right? This is what you're going to do. So the same thing is going to be done here. Just that the way we subtract is going to, you know, is going to be a little bit different than how would you do it in classical mathematics. I'll just write down the number as it is as of now, and I'll show you how to carry out this subtraction. There are some rules that you need to keep in your mind while subtracting binary digits. I'll also write down those rules for you. So please make sure that I'm not making a typo. I'll just copy it from here. So it is going to be 1 0 1 0 triple 1 0 1. So 1 0 triple 1 0 1. I hope I'm not making a typo. Please let me know in case I am. One of the numbers is 1 0 1 1 and 0 1 0 1 1 and 0. All right, so I'll just write down some rules for binary subtraction for you. If you are subtracting 0 from 1, then the answer is going to be 1 always. If you are subtracting 1 from 1, the answer is going to be 0. If you are subtracting 0 minus 0, the answer is going to be 0. Whereas if you're subtracting 1 from 0, the answer is going to be what? The answer is going to be 1. Or wait, 1 0 1. Yeah, the answer is going to be 1. But in that case, a borrow will be required. You will have to take a borrow from another binary digit. And once you take a borrow, what will it become is, it will become 1 0. So I'll just write it here for you. When a 0 takes a borrow, it becomes 1 0. And 1 0, what do we call it in binary? It becomes 2. And when you subtract 1 from 2, what do you get? You get 1. Right? So this is the logic behind it. When you subtract 1 from 0 in binary, you have to take a borrow of 1. As soon as you take a borrow, it becomes 1 0. 1 0 means 2. And when you are subtracting 1 from 1 0, that means when you are subtracting 1 from 2, you get 1 as the output. So these are the 4 rules that you need to keep in your mind while doing binary subtraction. All right, now I'll do that binary subtraction for you. So I'll write 1 0 1 1 1 0 1. This is the x plus y, or this is the sum. And then we have the actual number 1 0 1 1 0. So I'll start writing it from the right. 1 0 1 1 and then 0 1. Fine. So now, based on the rules that I have written here on the top, what do you think 1 minus 1 should be?
0.
It is going to be 0. Yeah. 0 minus 0, it is also 0. 1 minus 1, it is also 0. 1 minus 1, it is also 0. 1 minus 0 is what? 1
One.
minus 0. 1 minus 0 is 1. Now, 0 minus 1.
1 and a borrow.
Yeah, 0 minus 1 is going to be 1. So this 1 will be taken as a borrow here. So this now becomes 1 0, and you're subtracting 1 from 1 0, you get 1 as the output. Now, since this 1 is already being used as a borrow here, we are not left with any other calculations or any other digits here in this binary representation. So the final answer is this 1 1 0 0 0 0. So the answer is going to be 1 1 0 0 0 0, the first option. Is it understood?
Yes, sir.
Fine. Let us move to the next question. So select the decimal number for the signed magnitude binary number, this. So see, the question itself has made it quite easy for us. It has already said that the number is written or represented with the help of signed magnitude notation. And we know that signed magnitude notation says that if the MSB is 0, that means the number is positive. If the MSB is 1, the number is negative. And here, what is the MSB? Is it 0 or 1?
1.
It is 1. That means the number is going to be negative. That means it is either minus 15 or minus 30. First two options are already eliminated. Now we have to find out what the binary representation or what the decimal representation of this binary number is going to be. So what is 4 times 1? Can someone tell me? What is 4 times 1? Is it 30 or 15? So 4 times 1 is what? 1, 1, 1, 1. So it is 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 2 power 3 is what? 2 power 3 is 8. 2 power 2 is what? 2 power 2 is 4. 2 power 1 is what? It is 1. And 2 power 0 is what? Sorry, it is going to be 2. And 2 power 0 into 1, it is going to be 1. So 8 plus 4, 12. 12 plus 2, 14. 14 plus 1, 15. So it is going to be 15. So minus 15 is going to be the answer. Is that okay?
Yes, sir.
So what is the 2's complement of the binary number, this? So you are already given a binary representation. Probably some work has already been done by you. Otherwise, you would have to find out the binary representation from a decimal number. Right now, you're already given this, and you just have to find out 2's complement. So does anyone remember how do we find out 2's complement?
Inverse it and add 1.
Exactly. So I'll write down that number. Can someone please tell me that number? It's a long number. So yeah, better if you or someone of you can spell it out for me. So 0, 0, 1, 1. What are the next 4 digits? Zero, 1, 0, 0. 1, 0, 0, 1. And 1, 1, 0, 0. So we have to find out the 2's complement. So in order to find out 2's complement, firstly we have to find out 1's complement, or we can say we will invert all the digits. So while inverting, what we'll do is we'll say 1, 1, 0, 0. This will become 0, 1, 1, 0. This will become 1, 1, 0, 1. This will become 0, 0, 1, 1. And the next thing is add 1. So we are going to add 1 here, and let us see. So what is 1 plus 1 in binary? What is 1
0.
plus 1? It is 0, and 1 will be given as a carry. So again, we are getting 1 plus 1. 1 plus 1 is again 0, and 1 will be given as a carry. So this time 1 will be written as it is, and the rest of the things will remain the same. 1, 0, 1, 1, 1, 1, 0, 0. So please match the answer. We have 0, 1, 0, 0 as the last 4 digits. 0, 1, 0, 0. So B option is the correct option. 1, 0, 1, 1, 1. Yeah, fine. So B option is the correct answer, and I hope you all are okay with that. Quite easy. Okay, so now we have these algorithmic based questions. I think we have done a few of them in details in some of the previous session, but let me see how many of them we can repeat. Well, this is going to be an easy one. So what we are doing here is we are moving a value of 3 into a register R1. So R1 now has 3 value. Similarly, in the next instruction, we are moving a value of 8 into R2. So R1 is 3, R2 is 8. We are comparing R1 and R2. Well, the comments are already given for you, so you don't really need to remember these instructions by heart. It says compare the values in registers R1 and R2. So we are comparing 3 and 8. Jump to label 1 if R1 is less than R2. So what do you think? Is R1 less than R2 here?
Yes.
Yes, it is, because 3 is less than 8. Then we will have to move to label 1. And label 1 says that you have to move a value of 10 into R3 register, right? So 10 will be moved to R3. This is what it says. And finally, it asks you what is the final value stored in register R3. So what do you think? What is the final value?
10.
Exactly, it is going to be 10. I'm sorry. Okay. Now, the next thing is, this time we have a loop here. So let us see. We are moving a value of 10 into register R1. We are moving a value of 5 into register R2 and a value of 0 into register R3. Then we are having a loop here. And the loop says that add the value of R3 and R2 together and put the result back into R3. So this is what it says. Add the value of register R2 and R3 and store in R3. Store what? Store the result in R3. After that, you have to decrement the value in register R1 by 1. And then you will have to check for a condition, jump back to the start of the loop if R1 is not 0. Okay. So what you are doing is you are basically decrementing the value of R1 each time. So the very first time when you will perform this calculation, what will happen is R3 plus R2, what will it give you?
5.
It will give you 5. So the R3 also becomes 5 and R1 gets decremented by 1. So R1 becomes 9. 9 is not 0. So we will move to the start of the loop. That means again this. Now this time again we will do 5 plus 5 because R3 is also 5 now and R2 is already 5. So 5 plus 5 will become 10. And R1 will become 8. Again we will come back. This time 10 plus 5 it would become 15. R1 would become 7. Next time it would become 20. R1 will become 6. Then it would become 25. R1 will become 5. 30. R1 will become 5. I think I'm missing some calculations, so maybe you can just write it down here in the paint as well. Okay, so if R1 is 10 here, we get R3 equals to 5 and R1 is decremented by 1, so it becomes 9. So R1 is 9, we get R3 to be 10. R1 is again decremented, it becomes 8. Now that R1 is 8, R3 becomes 15 and R1 gets decremented, it becomes 7. Then R3 becomes 20 and R1 becomes 6. R3 becomes 25. I'm simply adding 5 because what you are doing is you are adding R2 into R3. R3 register's value will keep increasing. So R1 will become 5 here. R3 equals to 30 here. And R1 will become 4. R3 will become 35. R1 will become 3. R3 will become 40. R1 will become 2. R3 will become 45. R1 will become 1. R3 will become 50. And R1 will become 0. So as soon as the value of R1 is decremented by 1 and it becomes 0, it says jump back to the start of the loop is R1 is not 0. But this time the value of R1 has become 0. So once it becomes 0, we will exit out of this loop and we are being asked to find out the final value for R3 register. And what is the final value for R3 register?
50.
It is 50.
50.
Okay. All right. So this is again we are back to theory-based questions. So which of the following is responsible for managing the execution of programs and allocating system resources?
Operating system.
It is going to be operating system.
Compiler.
Sorry. Compiler is used to translate your program into a language that machine can understand. Debugger is something that we will be introducing in a later part of this course. How do you actually look for errors or bugs in your code? Whereas linker is something that is required at the execution phase of a program when you use library files like stdio or whatever you are working with in C. So the functions that you use from those library files, they are linked at the time of execution. So that is where linker comes into the picture. But as far as this question is concerned, operating system is going to be the correct answer. Which component of a computer system is responsible for directing the booting process?
BIOS.
This is directly being taken from the lectures again. So yeah, the BIOS, basic input-output system. And which of the following is machine independent?
High level language.
Exactly, high-level language. So the C program that I'll write on my machine can also work on your machine. Right? So click on check answer and OK. So all right, we got all correct. So please let me know if you have any questions from week 2 practice assignment. If no, we'll go to week 2 grid assignment. All right, I take that silence as no. So we shall move forward to week 2 graded assignment. Okay, so now we are given this decimal number of 113. So now that we already have done one such question before, I want you guys to work on this. Well, already the answers are visible, but still I want you to work out on this and find out what the actual representation of this 113 number is going to be. Can you all please do this? Meanwhile, I'll also set up my paint to perform these calculations in front of you as well. So the decimal number is what? It is 113. Right. So 1, or I'll write it here instead. 113. Okay, let us see. So 2, how shall I cancel it? What would be the quotient? What should be the quotient when you are dividing 113 by 2?
56.
Is going to be 56, and it will leave out 1 as a remainder. So 228, it is going to leave 0 as the remainder. Then 214, 0 as the remainder. 27, 0 as the remainder. 2 times 3, 1 as the remainder. 2 times 1, 1 as the remainder. So the answer is 1, 1, 1, 1 and 0, 0, 0 and 1. So 3 times 1, 3 times 0 and 1. So 3 times 1, 3 times 0 and 1. So second option is the correct answer, where we have just added one more leading 0 in order to make it an 8-bit representation. So second option is correct. Yeah, this is what you can see here. All right, I hope this is understood to all. So right now we are given a binary representation and we have to convert it into the hexadecimal. This is one of the easiest conversions that you will ever get. So binary to hexadecimal or hexadecimal to binary are the easiest ones, right? So what you have to do is you just have to create a group of 4 from the right hand side. So I'll create a group of 4. So I would consider 0, 1, 1, 1. So what do you think 0, 1, 1, 1 would be? What is the decimal equivalent to 0, 1, 1, 1? It is going to be 7, right?
Yes, sir.
Okay, so we just have to find out which all options have 7 as the last digit. First and second option have. So second and well, fourth option we cannot say. Well, just after looking at this representation, you would say fourth is not the correct answer. So second option is already eliminated after grouping the first 4 bits from the right hand side. Now let us take a group of another 4 bits. So 0, 1, 1, 1 is done. Now we will take 1, 0, 1, 0. So what is 1, 0, 1, 0?
5.
It is going to be 5. So even the third option is eliminated and the first option is the correct. So 157. You don't even need to do the rest of the calculations. We're straight away to the answer 157. Okay. Well, anyways, we are just left with this one bit here. That is 1. You will have to add 3 more leading zeros here in order to make it 4 bits. And 0001 is going to give you 1. So 157 is what you will get as the hexadecimal representation for this. What is the minimum number of bits required for binary representation of this? Can someone tell me how would you solve such questions? So you are given a decimal representation, and you have to find out how many number of bits you require in order to represent this decimal number in binary.
You can convert that into binary and then that will determine the bits.
Exactly, that is what you need to do. So 1001, well, it is going to be a long calculation. So let me just do it. 1001.
I think if everyone is fine, we can skip this, keeping
Yeah,
in
sure.
mind. Yeah. I mean, let's take the opinion of others as well.
I hope you all would be able to solve this question. We already have done 2 of such questions before. Yeah, I think that is okay. So consider a 10-bit. I think we already have done this question. Okay, previously it was for sign magnitude. This time we have for 2's complement. So this time we are given a 10-bit number, and we have to find out the positive and negative ranges. We are also, said that we are using 2's complement notation. So the advantage that we get for 2's complement notation is that one extra number can be included in the negative range. So positive range is going to go from 0 to 2 power 9 minus 1. That is okay. But negative range is going to be till minus 1 to minus 2 power 9. So second option is correct here. Yeah, second option is correct. The first option would have been correct for sign magnitude, but for 2's complement, second option is correct. I hope that is okay for all. Fine. So now question number 5, you have to find out the 8-bit binary representation of minus 34 using 2's complement notation. So let me see how many of you can get this done. What do you think? How would you do it? What are the steps? Does anyone know? How can you get this done?
We'll convert it into, base 2, but what is that 8-bit binary? Once you get in a binary, then it's easy to get into 2's. So can we try that at minus 34? Okay, it's minus 34. Sorry. Yeah, then also it would work, right? If we can just convert it into binary,
What would you convert into binary?
the decimal number, the minus 34.
So can you tell me what is the decimal or binary equivalent for minus 34?
Can't we just use the same division?
Oh, that is for positive numbers.
No, but you can carry the negative sign as well, right? I mean, I
No,
don't. Will
no.
that not work? Okay.
So does anyone know how do you solve such type of questions?
Or can't we make 34 positive side into 2 minus 1? 34 into 2 minus 1? And then work out its base 2? That's a long shot. I don't think that will work, correct?
Sir, we can convert only 34 and then put 1 at the last first. Put 1 for the negative side. Hello?
Yeah, I'm able to hear you. I think we lost.
Hi, am I audible?
Yes, sir.
Yeah. So what are you saying or what are you suggesting is for sign magnitude? Right? In sign magnitude, we change the MSB in order to represent what the sign of the number is going to be it positive or negative. But in this
Yes.
question, we have specifically said to find out 2's complement notation using 2's complement. All right. So for that, let me tell you how would you solve such type of questions. For that, I first wanted to let you know a general formula. Okay. So, as you know that what happens in 2's complement is we basically take all the negative ranges number and we put them after the positive range, right? This is how the professor demonstrated in the lectures as well. How these are things actually being represented in the computer's memory. So it becomes difficult for us to find out what the actual representation for this number is going to be in negatives. So how would you do that when you need to find out the decimal representation or even the binary representation? So let's say there is a number called x and you have to find out its binary representation. Well, this is a tough job. Just like you have this minus x, you will be having a number called x, right? So it is very easy for you to find out the binary representation for number x, right? For example, if you are given number minus 34, you can easily find out binary representation for 34, right? Plus 34. Is that correct?
Yes.
All right. So once you have the binary representation for the positive number, what you can do is you can take the 2's complement of that, and that would give you the negative numbers binary representation. You just have to take 2's complement. Right? Again, I would like to repeat. If you are given a negative decimal number and you are supposed to find out the binary representation for that, what you should do is you should find out the binary equivalent of the positive number and you take 2's complement of that. The vice versa is also true. That means if you have the binary representation for a number, let's say for a negative number, and if you take 2's complement of that, that is going to give you the binary representation of the same number's positive value. Okay, so now if we have to find out what this minus 34 in binary is, what would I do is I would first find out what this 34 is in binary, positive 34, and I'll take 2's complement of that. Right? 2's complement means I'll invert all the bits, I'll add 1 to it. Or yeah, I'll add 1 to it. This is how I would do it. So this is the approach that you should be following. Did you get it?
Could you please repeat the last step? So you take the positive and add 1.
You take the binary representation for the positive number and you find out the 2's complement representation for that. So let's say if I get 0, 0 or whatever it is, I just have to find out the 2's complement representation for this or 2's complement for this number. And how do you find 2's complement? You first invert all the bits and then you add 1 to that number. Are you getting it?
Yes, sir.
Okay, let me repeat it once again. If you need to find out the binary equivalent of a negative decimal number, what you should do is you should first find out the binary representation for the positive number. Once you have the binary representation for the positive number, you take or you find the 2's complement for that binary representation. And whatever you get as the result is going to be your answer. So for example, let me show you for 34. Can someone tell me what is going to be binary representation for 34? So it is going to be 1, 0, 5, 4, 3, 2, 1, 0, and 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be binary representation for number 34. Is that correct? Can someone please confirm?
Yes, sir, it is correct.
Okay, so this is for plus 34. Now what we have to do is in order to find out 2's complement, we have to invert. Right? So we will invert. For inverting, we will make this 0 into 1, 0 into 1, 1 into 0, 0 into 1, 0 into 1, 0 into 1, 1 into 0, 0 into 1. Now we will add 1. So for adding 1, we will just write 1 here and we'll do the addition. So 1 plus 1 will become 1, 0. 1 will be given as a carry here. We'll write it as it is. Then 1, 1, 1, 0, 1, 1. So this is going to be the binary representation for minus 34. It is what? It is 110, 1101 and 1110.
I think when you took the 34, there were the 2 leading zeros are not required, correct? When you
I just made it 8-bit. That's it. Yeah,
Oh,
they are
acha.
not required.
Okay, since the question demands it's a 8-bit, so you had to. Okay, got it. Okay.
So the answer is 1101 and 1110. Yeah, so 1101, 1110. First option is the correct option. I hope you all understood, right? The approach. How would you do that?
Yes, sir.
Yes, sir.
Okay, fine. So Next question is, which of the following statements is a true? Unicode is an encoding technique. Just give me a minute. Yeah, all right. So, okay. So Unicode as an encoding technique. How many of you do you agree that Unicode is an encoding technique?
No, it is.
No, it is not. Unicode is just a character set. It is not an encoding technique.
Oh, okay. UTF-8 is it? Okay.
UTF-8, 16, or 32, these are the encoding techniques for this Unicode character set. So ASCII can be said as an encoding as well as a character set, but Unicode is a character set alone. So first option is a false statement. Now UTF-8 is one of the encoding techniques to represent Unicode characters. That is correct. And UTF-8 is a variable length encoding technique. That is also correct. So second and third options are correct. First is wrong. So UTF-8 is one. Okay, UTF-8 is. Oh yeah, fine. So second and third options are correct here. All right. I think we already have a discussion on this question before. So I would not have a lengthy discussion right now, but uh, so you probably don't need these references as well if you need to find out binary representation for BAT, because if you know that uh, all are basically in lowercase here, so you must know that the lowercase representation starts from 97. So small a is represented with decimal number 97. uh, Similarly, small b will be represented with 98, small c will be with 99, and so on. Similarly, you can find out what the binary representation for the small t is going to be. But just to make your work easy here, what we have done is we have provided you with some references. For example, if you need to find out for b, you're already given the representation for b here. You just have to check that which of the representations is basically matching with this thing. Then you have for a. In order to find out for a, what you need to do is you just need to subtract 1 from the representation for b, because as I told you, the decimal equivalent for small a is 97, and decimal equivalent for small b is 98. So there is a difference of 1. So you just have to subtract 1 from this binary representation. Then you will be able to get decimal binary representation for small a as well. So what you can do is, for example, this second last bit that you have here as 1, you need to make it 0 and make the last bit as 1. This is what you would do in order to subtract 1 from here. So I hope with all these hints you will be able to guess the answer. So answer is already given here. Yeah. So do you guys have any questions with respect to this? Yes, guys, any questions, or shall we go ahead?
Sorry, what was that you said? The last bit, you just reverse it if you want to reduce 1.
Yeah, for example, this is 1 0, and you need to subtract 1 from it. So you would subtract 1, and since it is a 0, it is going to take 1 as the borrow from the next bit. So this will become 0.
Okay, got it.
Right. So just telling you that thing. Fine. I hope that is clear. So let's not spend more time here. So looking at this question, it is not zooming up. Okay. So what you are doing is, again, simple instructions. You are moving a value of 5 to R1. Then you are adding two values, R1 and 7, and you are storing the result back in R1. So 7 plus 5 becomes 12. R1 is now having value 12. Then you are moving that value of 12 to R2. And then you are subtracting 3 from that 12. So it becomes what? 9. And you are putting it back into R2. So the final value of R2 is going to be 9. That is simple enough. 5, 8, 10. So yeah, this is the question that I guess we have already done before. So I would like to skip that question. In case you have any problems with this, maybe you can come back to us later. But for now, I'm skipping this. Okay, move R1 7, move R2 0, move R3 1. Start of loop, compare the value in register R3 with the value register R1. Jump to the end if R3 is greater than this. Just a minute. Okay, so please tell me if we should be doing this question or shall we skip this as well? Does not seem to be a difficult question. So you just have to follow the steps. We have already tried one such question before. So yeah, please let me know if we should do it or we can skip this question.
It all depends on the probability of similar questions coming, in the re-attempt. So we would leave to you, based on whether there's a probability of it reappearing of the same nature.
Well, of course, the type of questions that you get here is quite possible that you get a similar question. Of course, not the same question. Definitely, you will not get the exact same question in any of your papers or exams. But yeah, questions based on similar lines is something that you would always expect. So it's okay, means I can go through this question if you guys want to do it. So please let me know which question shall I go through, 9th or 10th. They both are of similar nature.
10th, I mean, if everyone is okay. Yeah.
I think no one else is speaking except you. So maybe
Yes, sir,
shall go.
10th.
Okay, fine. So what we have here is we are putting a value of 7 in R1, a value of 0 in R2, and a value of 1 in R3.
Sorry. My bad. Because I just thought that you did the same thing, right? And every time you just increment one until you get to the level of zero, correct? No, I agree with you. It's going to be a repetition of what you've done earlier.
Okay, anyways, maybe we can just do one of these. Fine. We'll try to wrap it up quickly. So we have R1 7, R2 0, R3 1. I'll just write it quickly. R1 is 7, R2 is 0, and R3 is 2. Sorry, it is 1, not 2. Okay, so what we are doing here is it is a start of loop. Then we are comparing the values in register R3 with the value in register R1. So R3 has 1, R1 has 7, so they are both not matching. If R3 is greater than R1, so R3 is greater than R1, no. R3 is 1, R1 is 7, so it is basically less than R1. So what we should do is we will have to execute this add R2 R3. What will it do is it is going to add R2 and R3 together and put the result back into R2. Okay. So what will it do is R2 plus R3. I think it was R3. Huh? Okay, it was R2. So okay, fine. So we are asking for R2. Fine. So R2 equals to R2 plus R3. So the current value of R2 is what? It is 0. R3 is 1. So it becomes 1. So the new value of R2 is 1. But with that, we are also incrementing the value of R3 by 1. So if R2 becomes 1, the R3 also gets incremented by 1. And it becomes what? It becomes 1 plus 1. It becomes 2. Right? Now, since it becomes 2, it is still less than 7. So what we'll have to do is we will again have to execute add R2 and R3. So this time R3 will become what? 1 plus 1. So it would become, it would become 2. And this time R3 will also get incremented. So it will become 3. Next time, okay, this is R2. Sorry, I'm making these typos here. So R2, this time it will become 2 plus, okay, we are doing R2 plus R3. Okay, fine. I made a mistake here. Sorry. Let me do it again. Okay, so firstly we have to check whether R3 is greater than R1. So R3 is 1 and R1 is 7. So R3 is not greater than R1. So if that does not happen, we have to do R2 equals to R2 plus R3. So instead, what will I do here is I would like to mention these values here so that I can, update them frequently. R2 and R3. So R1 was initially 7, R2 was 0, and R3 was 1. Now with that step, what did we do is R2, we know it was 0. and R3 it was 1, so it became 1. And with that, we also incremented the value of R3. So it became 1 plus 1 equals to 2. So after the first iteration, R2 became 1 and R3 became what? R3 became 2. Now again, we will come back here and check if the value of R3 is greater than R1. So R3 is still 2, R1 is 7. So that is not greater. So we will have to again repeat this. So R2 equals to R2 plus R3. What is the current value of R2? It is 1. What is the current value of R3?
2.
It is 2. So 1 plus 2 will become 3. And R3 will be incremented by 1. So it is already 2. It will be incremented by 1. So it becomes 3. So R2 also becomes 3. R3 also becomes 3. Again, R3 is not greater than 7. So we shall execute this one more time. What is the current value of R2? It is 3.
3.
Current value of R3, it is still 3. So 3 plus 3 becomes 6. And R3 will be incremented. So it becomes 3 plus 1, 4. Again, 4 is not greater than 7. So R2 equals to R2 plus R3. This time it will become 6 plus what?
4.
4.
6 plus 4 becomes 10. So this becomes 10. And R3 equals to 4 plus 1, that is 5. Again, 5 is not less than 7. So one more time. So this time 10 plus 5, it becomes 15. And R3 is incremented 5 plus 1, it becomes 6. So it became 15, it became 6. Again, 6 is not greater than 7. So R2 plus R3. 15 plus 6 is what?
21.
Becomes 21. And R3 again got incremented by 1. So it became 7. Now see, watch this condition very carefully. It says jump to the end if R3 is greater than R1. Right now they both are equal, but still R3 is not greater than R1. Okay, so we have to execute one more time. So R2 equals to R2 plus R3. Then it becomes 21 plus 7. So it will become 28. And R3 becomes 7 plus 1, that is 8. So this time 8 has been, or 8 has become greater than 7. So we shall move to jump to the end. So we'll directly come to end, and it is asking the final value of register R2. So R2 has
28.
28. So 28 is going to be the correct answer, and yeah, it is. I hope you all understood.
Yes, sir.
Yes, sir.
Fine. So we are done with the practice and graded questions for week 2. Please let me know if you have any questions. If not, then we can start with the graded questions for week 2.
Just a suggestion. See, I think Saturday we missed that the session, right? So we will be left with only 2 now. While we have completed the week 2, there are similar questions in mock
Okay.
from week 1 and 4, because what happens is logically your week 3 and week 4 are more into the basic programming.
Yes.
So would you please consider picking up the week 1, week 2 questions in the mock and closing that off, so that that is taken care of, and the next time we could look into week 3 and week 4, if that's fine with everyone.
Yeah, sure. I don't have any issues doing this.
Thank you.
Okay, fine. Not a problem. All right. So we have to focus on the questions that are related to week 1 and 2. I guess majority of the questions will be from those 2 weeks. So yeah, let us do those. So first question is, of course, from the first week. So let R0 be a register and M0 be a memory location. Consider the following 2 instructions. Here, what you are doing is you are trying to load something from the memory into register. So whenever you are trying to copy a value from memory to a register, it is known as load operation. Why load? Because you are loading it into register for performing some calculations, right? And when you are done with the calculations, what you generally do is you put back those values into the memory from where you picked. So this is known as store operation. So if You are taking values from memory, copying them into register, that is known as load. If you are copying from registers, putting them into memory, that is known as store. So the first instruction here, or first statement here, it is basically doing load operation because it is taking value from memory to register. So instruction 1 is a load operation, whereas instruction 2 is a store operation. Yeah, that is first option itself is correct. I hope you are able to understand what I'm trying to tell you.
Yeah, thanks.
So which component of a computer system is responsible for non-volatile storage of data and programs? What do you think?
Secondary memory.
Exactly, secondary memory, because all others, well, there are only three types of memory that we are able to see: main memory, secondary memory, and registers. CPU is not, of course, a memory. So registers and main memory, they both are volatile memory. As soon as you turn off your computer, shut down your computer, they both will be lost. So second memory is the type of storage that is persistent in nature. Okay, so I should select this secondary memory. So which of the following examples of secondary storage devices in a computer system? Well, secondary storage devices. So SSD, what do you think?
Yeah, second.
Yes, of course
SSD,
it is.
hard drive, USB.
RAM is not, register is not, cache is not. So first three options are correct. So how many bits are required to encode a string IITM using 7-bit ASCII? You have already mentioned that you have to use 7-bit ASCII because ASCII also exists in 8-bit. So you have to use 7 bits here. And since there are 4 characters and each character is going to require 7 bit, so 7 times 4 is going to give you 28. So 28 bits is what you need in order to represent IITM. I hope that's okay. Sorry. Did someone say something?
Could you please come again on this question 4, please?
Sure. So you are supposed to use 7-bit ASCII here. And what happens in 7-bit ASCII is every character takes 7 bits in order to encode itself. So here we have 4 characters. One is I, other one is I, then T, then M. So we have 4 such characters, and each of the character is going to take 7 bits. So 7 times 4 is going to give you 28. So 28 bits are what you need to encode this IITM string in the computer memory. Which component of computer system is responsible for fetching instructions from memory and executing them? What do you think?
CPU.
Exactly, it's CPU. I shall skip the 6th question. Data types, did we do it in second week? I don't know whether you guys would be able to.
Yeah, this is the week 3, I think so. 7.
Question 8, question 9, okay, question 10. Yeah, this is something we can try. So what is the range of values? Okay, this is also coming from week 3. This is from week 3 or 4, 3 or 4, 3 or 4. Don't we have any more questions? Is it? Operators are also from later weeks. So consider a decimal number 108. I don't think we need to do it again. We have already done enough questions for decimal to binary conversion. And the same with this as well. We are given binary representation. You have to find out hexadecimal. What you have to do is you have to create group of 4 bits from the right hand side. The first group is going to be 1011. So what is 1011? It is going to be 11. And 11 means B. 11 in hexadecimal means B. So you have to find out options which have B at the end. So first and second options, third and fourth are eliminated. Then you take the next 4 bits, 1001.
9.
So 1001 is what? 9.
9.
So 9. So you're only left with this second option here. All others are eliminated. So yeah, we only have these many questions in the mock exam based on weeks 1 and 2.
Yeah, that really helped. Could we do the same thing for the exam for itself?
Which exam?
I think the answer key for exam, right? The one that happened on 6th of August.
Okay, can I get it from here?
Yeah, and hope that this session is getting recorded, correct?
Yeah, it is getting recorded.
Okay. Hard time finding the previous session. Probably that has to be posted.
No, the recording link is already provided.
Is it?
Isn't it visible?
Okay.
Can you all please check once? I think the recording link has already been appended to the calendar invite.
That's what I didn't say. Maybe it's just for me. Probably the others can confirm whether they've seen that link.
Can someone please confirm if you are able to see the recording link from the previous session?
Okay, let's just continue. Probably they'll come back later.
Or I'll check it from my end. So Friday was the session. Revision session 1. Yeah, so you can see this recording link is here.
Yeah,
I hope
maybe
you will
I'll-
also be getting such type of boxes in your calendar if you have added that.
Sure. That's taken care of. Fine.
Okay, fine. So where are we starting for C? I think C is the last. C is last only.
So we would expect a sort of a similar kind of a paper, correct, in the reattempt?
What do you mean by similar kind here?
The nature of questions.
Nature of questions, of course, is going to remain same.
Okay.
Okay, fine. So this is the start for C question paper, I guess. So consider computing the product of 10 values stored at memory location M0 to M9.
I'm
The
sorry
result-
sorry to interrupt, but if the solution is available somewhere, there's no point. I mean, we can definitely go and refer to that.
Solution is not available. Only the answers can be seen.
Acha. So in that sense, maybe what would be also useful to others is if the solution can be put into your writing pad and saving it. Probably others would want to refer to it as well. If there's something that could be considered.
If there is a question that would require some calculation or
Yeah,
something,
correct. Anything that can be straightforward, we just can discuss it. Yeah, sure. Thanks.
Okay, so we have to store the result at M10 memory location. We are given 3 registers for some internal processing, temporary processing, R0, 1, and 2. And we are also given these steps. We just have to predict the missing step from here. So R0 is initialized with the value 0. So it is probably going to be a counter for us that is going to help us in keeping track of how many memory locations we have visited so far. R1 is 1. So this is going to be the actual variable where we are going to store the result, the product. And R2, it is going to keep fetching values from the memory. So right now the value of R0 is 0. So it is going to get the value from M0 location. The next time when R0 will be incremented by 1, it will fetch the second value from the memory location. So we just have to find out what should you fill in the 6th place so that the algorithm is completed. What do you think? Looking at these options, well, the answer is already visible to you, but why you should be checking for R0 should be less than 10. The reason is the R0 was initialized with the value 0, and in order to operate for 10 iterations, the maximum value the R0 can hold is 9, right? Because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 is going to be the 10th iteration for this algorithm, and that is all what we need because we have 10 such memory locations, M0 to M9. So we just need to go till M9, right? We don't have any, M10 or any value stored at M10. M10 is supposed to be where a result should be. So we have to check whether R0 is less than 10 or not. Or you could also say less than equals to 9 or less than 10. They both are okay. But the next question is, should you go to step 4 or should you go to step 3? That is the main question that you should try to understand here. Now, of course, the answer says that you should go to step 3. My question is, why should not you go to step 4? Can anyone answer why should not you go to step 4? Why should you not skip this step 3 here? The reason you should not skip this step 3 every time the value of R0 is incremented is because R2 or step 3 is the instruction where you are trying to fetch the actual value from the memory. For the first iteration, you would only fetch the value for M0 location. But when R0 is incremented, you have to make sure that you get the next value from the memory, that is M1. But if you skip this third step and you directly execute fourth step, what will happen is it will keep on operating with the value that is stored at M0. Because in the first iteration, R2 would have gotten value from the M0 memory location, and that is all it will have always. So it is essential for you to keep updating the value of R2 register from the different memory locations M1, M2, M3 till M9. Right? So that is why this is the correct condition.
Still not clear about that. R1 is sort of equal to 1. That should save the sum. R1, the row 2 or line 2. What is that doing?
R1, we are just initializing it with the value 1. So see, since we have to find out the product, we have to initialize it with some value. So that doesn't matter with what number it is multiplied with. It should always result the same number. So see, if you are multiplying R1 multiply R2, let's say the first number is 5. So in order to store 5 multiply 1 equals to 5, you have to make sure that it is 1. If you will initialize it with 0, the answer would become 0.
Okay, it could actually be any number.
No, it could not be any number. It must be 1.
Just for, let's say you take 2. Even that also would serve the purpose there, correct?
No, that would not. See, let's say the number stored at memory location M0 is 5. What you are doing here is you are multiplying R1 into R2. R2 is what? R2 is going to be 5, right? Because that is what you have fetched from memory. And if R1 is 2, what you are doing is you are saying 5 into 2, that becomes 10. So what you are saying is that the product till the first number is 10. That should not be the case. You have only fetched one number from the memory so far, and the result, the product should be the number itself.
Maybe I'm still not, because it says the product of 10 values, so it could be something, right? So you're telling that if I put anything apart from 1 on, what you call it, on point 2, it will give a wrong input.
It will give a wrong output, yes.
Output, sorry. Okay.
Which of the following typically provides the fastest access of data to a CPU? I hope this is an easy or straightforward question. Registers are what are closest to the CPU, and that is where you will get the fastest access. I think this is a similar question, right? We already have tried 2 such questions before in the today's session. So what you are doing here is you are moving the value 10, initializing R2 with the value 0, compare the value in register R1 with 0. If it is 0, then you are moving to the end. Else what you are doing is you are simply adding those values. So what you are doing is you are essentially finding out the sum from 10 to 1. So the answer should be 55. So this is what this algorithm does. It simply adds up all the numbers from 1 to 10. That's it. I hope I don't need to do it in Paint, right? You should be able to do it yourself.
Yeah, agree. Good.
So how many characters can be encoded using 4 bits? We have done questions on similar concept. If you need to find out how many characters can you encode if you are provided with some number of bits, you just have to put that as the power of 2. So 2 power 4 becomes 16. That is what the answer is. 2 power 4, 16 characters. So which of the following terms describe the process of starting a computer system and initializing its hardware and software components? This question has been directly taken up from the recording or from the slides. So bootstrap is what the process is called. The other name for that same process is booting as well.
No, I think this is where I got. What's the difference between these two?
They both are same, synonymous terms.
Okay, there's no difference, right? Absolutely different.
Yes.
Okay, got it.
What is the 2's complement representation of the decimal number? -7. So we have done a similar question. The number that time was minus 34. This time the number is just minus 7. The approach that you should follow for this is you first have to find out the binary representation for positive number 7. You have to find the 2's complement for that. And then you will get the binary representation for minus 7 as well. So I hope you can do it yourself, or else I can simply do it in Paint as well if you want. Won't take much time. What do you guys say? Okay, maybe I can do it. So 7, we have to find out representation for 7. What will I do is I will first find out the binary representation for 7. What it is going to be? It is going to be 0, 0, 0, 0, 0, 1, 1, 1. If I invert all the bits here, they will become 1, 1, 1, 1, 1, 0, 0, 0. Then I have to add 1 to it. So I will add 1 to it. It will become 1, 0, 0, 1, 1, 1, 1, 1. So 5 times 1, 2 times 0, and again 1. So 5 times 1, 2 times 0, and 1. So I hope that is okay. That is okay. Shall I move forward?
Please.
So Dash is a program used to translate the human readable code into machine interpretable code. So compiler, this is what we discussed while discussing one of the previous questions as well. I think the options are the same what we had for that question too. Anyways, yeah, compiler is the program that does that. We can skip this. We can skip this. Assignment operators. Okay, this will also be introduced in a later week. This is word mass. This is operators. These are for loops. This is again a program. This is also a program. This is also a program. Okay. So consider a decimal number 98. What is the 8-bit binary representation? We have already done it quite a many times in the today's session. So maybe we should not repeat it. I hope you guys will be able to do it yourself. Okay, so if we have to find out the binary representation for this, hexadecimal, we have to create groups of 4 from the right hand side. So 1, 1, 1, 1 is going to be our first group. So all ones means we are going to get F. Let us see how many of these have Fs. So first and second options are still in the race. Third and fourth are eliminated. After the first group 1, 1, 1, 1, we have the second group as 1, 0, 0. So that means it is going to be 1. So we have to check which all these numbers have 1 as the second digit. So only the first option has 1 as the second digit. So this is the 1. That is the correct answer. The second option is also eliminated. And yeah, that's it. Nothing else.
No, I think this was really useful. Taking considerations was the revision class. And what is observed is that there's a lot of repetition of at least the similar nature of questions. So you must have guessed the next question. Will this be extrapolated to the reattempt?
Maybe to some extent, but you might see that some questions will be directly related to what you got in the previous one or in this qualifier exam, but not all. Of course, the majority of the questions will be, of course, different, as you can expect a few questions to be based on almost similar lines.
Okay, fine. And can we quickly recap? Based on today's discussion on week 1 and week 2, anything you would like to conclude?
Let me look at the lectures.
Yeah, thanks.
Okay, so week 1, I would say that it is all related to theory. I don't think there is much logical, at least as far as the week 1 is concerned. We have this split memory architecture. Okay, that is where we try to split the main memory and try to use the registers so that we get the fastest access to the values and we can do the fast processing. Loops, conditions, and branchings. This is just a theoretical concept that was introduced in this week, just to let you know what the concept of loops is, in case you want to repeat certain statements again and again. And that is where loops will come into the picture. Conditions and branches, how these things are maintained within the programs. Definitely, you will get to know about these when we will start the formal programming from week 3 onwards. So week 1, I don't think I have uh, much to say about. It is all theory based, so you should just be going through all the lectures probably at 1.5 or 2x speed, and I hope that should be sufficient enough. Whereas week 2, there are a lot of things that you probably have to practice. Of course, the very first thing is going to be the number system. There are 4 types of system that we have: decimal, binary, hexadecimal, and octal. Hexadecimal has base 16, binary has base 2, octal has base 8, and decimal has base 10. You must know how you can go from one system to another. For example, if you are given a number in octal system, how would you find out the binary representation for it, or decimal or hexadecimal? The same applies for all other types of number systems that you have. This is something that you must know, and for that we have done this thing in detail in one of the previous sessions that was done during the qualifier batch itself. You of course will be able to access the recording for that session, and I think that is all what you need to do. So please do enough practice for that, because in the question paper you saw that we are having at least 2 questions based on number system in every question paper. One was for decimal to binary, other one was for hexadecimal to binary, and another one was based on 2's complement notation. So right, these 2 or 3 questions I would say are very important things. So please go through that entire session and be thorough with what the approach should be in case you want to go from one system to another. Floating point, it is required only as far as the theory section is concerned. You won't be getting any practical based questions based on these kind of representations. Character representation and encoding, ASCII, Unicode, what all different types of encoding do exist for such type of character sets, what is the difference between them? These are the things that you must know. Then instructions, of course, we have done a lot of assembly level programming, or we have at least seen a lot of assembly level programs, though along with the instructions, we have also been providing the comments for your better understanding. So definitely you can expect at least 1 or 2 questions based on this concept, where you will be given an algorithm and you will have to probably find out what is going to be the final value that will be there in a register, or you will probably be given an algorithm where one step is going to be missing. You will be required to predict the missing step. Such type of questions could arise from this instructions topic. Program and role of operating system, at least as far as the week 2 is concerned, again this is going to remain theoretical. What all are the roles of an operating system in a computer system? So these are things that you must be knowing. Program compilation, so I'm not sure if we have discussed about the different steps that happen while executing or while the program is compiled into machine level code. So if those are not discussed, then you should not be worrying about that. So program compilation is probably just a high level overview of how a computer system basically interprets this. So professor would have probably shown you different types of codes that the computer tries to allocate to each of the token or the identifier that you use in the program. So again, not something that you will be tested on practically here. You should be just knowing the theory concepts related to it. And role of operating system, we have already done that. Yeah, I think that's all. You don't see any other thing here. So the 2 most important topics that I could say from week 2 are number system, conversions from one system to another, and the character representation and encoding, along with the algorithms. That's it.
Excellent. Just wait for if there's anything from the other participants as well.
Anything else, guys? Okay, so since we are recording it locally, just like I have provided the recording link for the previous session, the moment we get the recording for this session as well, because it takes some time to process the recording, and then we get an email for that. So once we get that email, I'll add it to the calendar invite.
So just planning ahead now, in the next, it's good to come prepared with the week 3, correct? Now with the core the basic
better you
program.
come prepared with your queries as well. So we can directly take up those queries that you have problems with. and then we can utilize the rest of the time discussing about some other concepts that you are struggling with.
Preferably let's go the same way, no? The practice and the graded week
Yeah, if you
3.
want us to go that way, of course, that is the simplest approach that we can follow. But okay, fine, fair enough. That is okay, fine.
And when can we have this, the next session? Can you please confirm so that, we
Even
also
we got confused the last time, last
No issues.
Saturday.
Such
Because
things happen.
I
Sir.
and Arup sir, we both were ready to take the session, and then we went onto the calendar and saw that there was no session planned that day. So
No,
even,
I think everyone needs a good long weekend. We understand. Yeah.
no, I mean we both were ready that time.
Agreed.
We
No
got to
issues.
know that there was no session planned that time. So yeah, I think it is gonna happen on Friday then. Friday 8 to 10.
Excellent. So would we take that would be the last session?
Is that the last session? Probably yes.
Ah,
I
then
don't see
it's
any other session planned.
then it's better to sort of club week 3 and week 4, correct? Together to one.
Yes.
So maybe we need to plan the time accordingly. Maybe 1 hour for week 3 and the second hour for week 4. Sure. Okay. Thank you
Okay,
so much.
So
Yeah.
I'll stop the recording for the session.
Okay. Now, if you can just give some tips as we go to week 3, week 4, knowing that it is not going to be a programming one. How do you think, in the short term that we have, we can prepare better?
Prepare better for.
Week 3 and week 4.
So week 3 is where we formally introduce the programming, right? Programming starts right from week 3 only.
So I was just looking at, I think there's a lot of emphasis on understanding the priorities, that BODMAS and the kind of, what do you call it, the precedence, or, that would definitely be something like that, some.
There are just a couple of rules that you need to remember. Everything else is sorted based on those 2 rules. That's it. Because you will be asked questions based on arithmetic operations only. Of course, you won't be asked questions on other type of operations that have to be performed where operators of different precedences or even the same precedences are involved. So there are just 5 arithmetic operators that you need to keep in your mind: plus, minus, multiply, divide, and what is the last one? That is modulo division. So plus and minus, addition and subtraction, they have the same precedence. And then multiplication, division, and modulo division, they have the same precedence. Just that the 3, multiplication, division, and modulo division, have higher precedence than the other. So if you encounter multiple operators with the same precedence, then you have to follow the associativity rule. And the associativity rule says for all the arithmetic operators, you have to go from left to right.
Left to right. Okay. Got it. Yeah.
Okay, so that's it from my end.
Thank you so much. This was really helpful.
All right, so I'll stop the recording for the today's session. I'll make it available